No doubt there is a smear here, so it's, as a matter of fact, testing essentially the earliest structures we know in the universe. This sort of information arrives in a negligible part of the time that we were previously aware of. So, I think part of the records we have in the current-day universe is going to be broken soon. A notable Nobel Prize winner says that the James Webb Space Telescope has recently discovered something bizarre in the universe, and the changes that are coming may not even be something we are prepared for. The latest discoveries are troubling for science. Increasingly insane things are happening, as the James Webb Telescope has uncovered a new impact that is turning our physics books on their heads. Adam Reese, a cosmologist and Nobel Prize winner, has long believed that science is on the verge of a crisis. There are numerous perplexing issues that are growing consistently, according to analysts. Can we still figure out what's going on, or is the field of science over? Adam Reese is likely one of the few experts who remain calm nowadays. Things are not the same as they were before the James Webb Space Telescope was launched. Seems likely that the universe is much older than we thought. Galaxies have formed much faster and in entirely different ways than we anticipated, and the universe may not be expanding from a single point. What should we do now if dark matter was just a misstep? The James Webb Telescope is already showing us the next image of strange occurrences in the universe. One of the most proficient individuals studying how the universe is expanding is Adam Reese. His work, which revealed that the universe is expanding faster than previously thought, changed the way we think about the cosmos and was a major part of the Hubble excitement. For years, Reese has worked tirelessly. He knows that our understanding of the universe is flawed, which is why he is excited about the telescope's recent discoveries. He helped examine the universe using supernovae as standard candles for the first time. Scientists use large-scale measurements to gauge how far and how fast objects move. Standard candles like these were incredibly accurate, but there was still one issue. Reese and his team found that the universe was expanding in some regions more than others, which contradicted expectations. During their work, another revelation emerged. Reese's measurements significantly differed from those based on the redshift method, which should not have been the case. This discrepancy is now called the Hubble tension. Reese, along with his colleagues Saul Perlmutter and Brian Schmidt, won the Nobel Prize in Physics in 2011 for discovering that the universe is expanding faster than expected. Schmidt and Reese are part of the High-Z supernova search team, which seeks to improve distance measurements in the universe. Perlmutter, on the other hand, reached similar conclusions at around the same time. They observed Type Ia supernovae, extremely bright stellar explosions that are useful for determining distances in the universe. These findings shocked everyone by showing that the universe's rate of expansion is increasing rather than slowing down, contrary to earlier assumptions based on gravity's pull. The concept of an isotropic universe, where the cosmos looks the same in every direction, is now in question. Adam Reese and other researchers initially supported the isotropic model, partially based on supernova observations showing uniform expansion rates. However, the James Webb Telescope's findings indicate that the universe may have evolved much faster and earlier than previously believed. The idea of dark energy, a mysterious force thought to drive the universe's accelerated expansion, has also been challenged. Dark energy, which makes up 68% of the universe's energy, remains poorly understood. Yet, new observations suggest the standard model of cosmology may need a complete overhaul. The James Webb Space Telescope has provided unprecedented precision in studying the early universe, hinting at phenomena that contradict established theories. Scientists like David Gross, a Nobel laureate in physics, view these challenges as opportunities. Gross believes the answers to the universe's biggest mysteries lie in the small-scale details rather than the large-scale picture. His work in string theory and strong interactions underscores the need to rethink our fundamental understanding of the cosmos. David Gross, who won the Nobel Prize in 2004 for discovering asymptotic freedom in the theory of strong interactions, emphasized that breakthroughs often arise when established frameworks are challenged. The findings of the James Webb Space Telescope, JWST, may serve as a catalyst for a new era in cosmology, requiring scientists to revisit long-standing assumptions about the universe. The standard model of cosmology, while groundbreaking in its time, was built on the notion of dark energy and dark matter, concepts that account for phenomena we cannot yet fully explain. Dark energy is thought to be the force driving the universe's accelerated expansion, while dark matter accounts for the gravitational effects observed in galaxies and larger structures. However, the JWST's observations of early galaxies and structures suggest that these models may not fully capture the complexities of the cosmos. If the universe's expansion is faster or its age is different from what we thought, this raises fundamental questions. What is the true nature of dark energy? Was dark matter misunderstood, or does it even exist in the way we imagined? The James Webb Telescope has revealed galaxies forming earlier and in different ways than expected, throwing the Big Bang timeline into uncertainty. Adam Reese and his colleagues are actively analyzing these new data, comparing them to prior observations, and attempting to reconcile the discrepancies. Meanwhile, other researchers are developing alternative theories. Could there be unknown forces or dimensions influencing the universe? Could quantum mechanics, which governs the subatomic world, hold the answers to these cosmic puzzles? The implications extend beyond cosmology. If the universe's fundamental laws need revision, this would ripple through physics, affecting fields like particle physics, relativity, and even our understanding of time and space. Scientists are optimistic, viewing this as a once-in-a-lifetime opportunity to rewrite the textbooks and advance human knowledge. However, caution is essential. The JWST is still in its early stages of exploration, and more data are needed to draw definitive conclusions. Researchers around the globe are working tirelessly to analyze the telescope's observations, while theoretical physicists are racing to propose new models that could explain the anomalies. As humanity stands at the brink of a scientific revolution, the excitement is palpable. The mysteries of the universe, its origins, composition, and ultimate fate, are closer to being unraveled. But for now, we must wait for more discoveries from the James Webb Space Telescope and for scientists to piece together the puzzle of the cosmos. The journey to understanding the universe is far from over. With every new finding, the cosmos becomes a little more intricate, a little more beautiful, and a lot more humbling. What lies ahead is uncertain, but one thing is clear: the universe still holds countless secrets waiting to be uncovered. Significant for learning about how stars act, plugs are the building blocks of protons and neutrons. The typical model of molecule physical science is in light of these particles, which are the structure blocks of all that we can see and gauge in space. On account of this, the fundamental designs and rules of the cosmos should likewise exist in the subatomic world. In addition to other things, Gross assisted with coming up with ideas about what happened right after the huge detonation. In those days, there were no stars or different things on the planet. For a huge number of years, there was just an extremely hot, early-stage soup where particles could move around without staying together. It's possible that before the huge explosion, there was a kind of quantum vacillation where all structures offset each other to the point where they were actually equivalent to zero. This quantum variance broke separated with the huge explosion, and particles full of charges and powers shot into a space that wasn't there before. Eventually, these pieces moved toward universes, planets, stars, and living things like us. Should we accept Gross when he says that these particles hold every one of the responses? Most likely, yes. But how might we study how particles act 13.8 billion years ago when they were in space? The microwave background energy from space is one thing that scientists utilize. This is remembered to be a very decent depiction of what happened just after the Big Bang, and it has likely changed a lot from that point forward. Quantum physicists and classical physicists don't exactly agree on the most efficient method to comprehend this record of the early world. However, in the realm of science right now, quantum and molecule physics and standard cosmology can't be set up. Quantum physics doesn't concur with what we are familiar with matter, or maybe the missing connection is quantum physics. David Gross is certain that this extension can be tracked down in particles and powers that we had barely any familiarity with before. He was one of the specialists who worked hard to get individuals from various fields to settle on something before James Webb began the discussion. He endeavored to connect quantum physics and general relativity, which he co-wrote so that they checked out together. He wanted to overcome any issues between these two logical fields. Gross' work on mimetic opportunity shows how stars act when their energies are exceptionally high. This is very significant for understanding the early world just after the Big Bang, when energies were extremely high. His ideas can assist us with understanding pieces of the development of the world that we don't completely see yet. That being said, there is some conflict among researchers because numerous traditional physicists imagine that string theory ideas are excessively difficult to trust. David Gross thinks that the quantum changes in the microwave foundation hold the solutions to every one of the inquiries that haven't been tackled yet. It's called the astronomical microwave background, CMB, and it very well may be seen as everywhere on the planet. From 1989 to 1993, the vast Foundation Traveler satellite was in orbit. It was the first to see little changes in the radiation's temperature. The Wilkinson Microwave Anisotropy Probe investigated these progressions from 2001 to 2010 to see if they showed evidence of the Big Bang. The BORD satellite has recently made one of the most intensive maps of the CMB scene. However, analysts are still not certain how to analyze this information. Some researchers say they have tracked down evidence of the Big Bang in the CMB, but others think it shows impacts with different universes and the presence of a multiverse. The investigation of the early universe is no simple accomplishment, and as additional information comes in, it progressively challenges existing speculations. Researchers working with the James Webb Space Telescope, JWST, are uncovering new hints that appear to go against the well-established comprehension of infinite development. One key area that remains a secret is the idea of dark matter. For quite a long time, physicists have trusted that dark matter is answerable for giving the concealed gravitational draw that holds cosmic systems together. However, later perceptions made conceivable by the JWST propose that dark matter may not be as pervasive or as powerful as once thought. The discoveries from JWST have, moreover, started to reshape how we might interpret the inestimable voids that exist between cosmic systems. These voids were once accepted to be unfilled locales of room, ailing in matter. However, novel perceptions are beginning to show that these voids may not be totally without any trace of issue, but rather contain stowed-away designs and inconspicuous types of energy that are not noticeable by customary means. This could substantially affect our thoughts about how the universe is organized on a huge scale. Another continuous riddle is the job of black holes in forming the arrangement of galaxies. While black holes have for some time been known to exist at the centers of most galaxies, the specific connection between these very huge objects and the universes they occupy is still not completely understood. Some speculations suggest that black holes play a basic job in managing the development of galaxies, while others propose that their impact is more limited than recently thought. The perceptions made by JWST could assist with explaining this issue by giving a more detailed glance at the conditions around black holes, especially during the early phases of galaxy development. As these new revelations unfold, researchers are increasingly going to computer simulations to assist with figuring out the data. These simulations attempt to reproduce the states of the early universe and explore how different forces like gravity, dark energy, and radiation collaborated to shape the universe. By contrasting these simulations with the real perceptions being made by telescopes like JWST, specialists desire to pinpoint the truth that has led to the present status of the universe. One of the most thrilling possibilities in the area of cosmology is the chance of finding altogether new types of issue or energy. For many years, researchers have theorized that there might be something else to the universe besides what we can currently identify. Whether this implies finding new particles, types of radiation, or totally obscure forces, the potential for earth-shattering revelations remains high. As technology improves and more data is gathered, researchers are confident that it will uncover secrets that have remained concealed for quite a long time. The emerging discoveries from the James Webb Space Telescope are also challenging the very foundation of cosmological models that have been set up for a long time. One of the most baffling inquiries being raised is the potential for multiverse hypotheses to find support in the data. The thought of a multiverse, suggesting that our universe is only one of many existing in parallel, is a questionable and speculative idea in physics. However, some recent discoveries like peculiarities in the vast microwave background (CMB) radiation are making researchers rethink the possibility that we may not be living in a singular universe but rather part of a much larger infinite structure. Moreover, the idea of cosmic inflation, which states that the universe expanded dramatically in the first fraction of a second after the Big Bang, may also need to be reconsidered. Some of the observations from JWST suggest that the early moments of the universe may have been significantly more complex than previously imagined, with possible fluctuations in the rate of inflation or even different inflationary events occurring in various regions of space. If confirmed, this could radically change how we might interpret the birth and evolution of the universe, suggesting that inflation may not be a universal phenomenon but something that happened in limited regions, leading to different pocket universes. Another key development is the advancement made in understanding the early development of stars and planetary systems. JWST's capacity to peer further into space than ever before permits astronomers to witness the formation of these celestial objects in extraordinary detail. Observations are uncovering that stars might form in ways that deviate from current models, showing that we still have much to learn about the processes that lead to star birth and the conditions that make life possible in the universe. As these secrets unfold, the scientific community is entering a new era of discovery, one that promises to rethink the limits of what we know about the universe and our place within it. The questions raised by these discoveries are just the beginning of a journey that may reveal even more astounding insights about the universe.